everybody. Thank you for coming today. Thank you for joining us. I know I'm excited because I'm not an insider on AI or on hardware. Coming from the open source professional services world and software world, this is a really exciting topic for me because I wanted to understand more about the engines underneath the hood of what is becoming the most fascinating subject these days. So thank you for joining us. Thank you. So forgive me, I am going to read from some notes because I'm still learning so much. But as AI becomes foundational and the infrastructure supporting it is under this intense pressure, while the market conversation is often dominated by a single player, a more nuanced and critical story is unfolding around the need for silicon diversity. The question for all of you, please take one at a time. Maybe we can start with Siona. The current market for AI accelerators is heavily concentrated. From each of your unique perspectives, why is fostering greater silicon diversity so critical for the future of AI development and deployment?
Hey everyone, my name is Siona. Just by way of an introduction, I lead the hardware engineering team at Cloudflare. For those of you who may not know, Cloudflare runs about 20% of the world's internet, and we do it through an interconnected global network that's more distributed. So I'm saying this just to lead to, we have colos all across the world in over 300 cities, and you can imagine the power constraints, the operational burden that comes with, right? So we have unique challenges of distributed inference and distributed compute and storage to deal with. So from a supply chain and reliability perspective, it makes a ton of sense to have a diverse silicon portfolio,
right.
But it comes with a lot of trade-offs from a real-world perspective. Things like every new SKU introduced into an architecture that spans a global 300-city colo is not easy to manage. There are issues with new SDKs based on the silicon provider and the telemetry associated with it. And of course, the performance tuning piece, which if you've worked on a CPU or a GPU, you know out of the box doesn't operate the way that it's advertised. It takes a lot of work and tuning to get there. So each new solution needs to be traded off with all of these variables.
Wow, okay, thank you. Hari, what about from the Meta point of view?
Hi, I'm Hari Krishna. I'm a tech lead for custom silicon development that is used in Meta's infrastructure, primarily to accelerate our workloads. From the challenges point of view, really when we look at this infrastructure, the biggest thing is really deploying this at scale, running them at reliably 24/7, and more importantly, keep improving the performance per watt, I think, right? Because we are looking at very, very huge investments. So from the reason today, right, when we have only a single player, that player typically what happens is it's a pretty generic GPU kind of a work system. So it's not optimized for the very specific workloads. There's a huge opportunity when we diversify the silicon primarily because once we start diversifying, we could actually super optimize for the custom workloads. And then the more importantly, the metric, the perf per watt, actually we can see huge multipliers there. So that's a real thing which is driving the diversifying the silicon there.
I see. Okay. And Kevin, what about at Vultr?
So for those of you that don't know Vultr, we're the world's largest independently held private cloud company with operating over 32 data center regions around the world. We're specialists in AI infrastructure, partnered with both NVIDIA and AMD. And from our perspective, diversity matters in all things in life. Diversity is what drives innovation. And there's really three core aspects of silicon diversity that really is top of mind for us. First and foremost is innovation. We're only seeing an acceleration of roadmaps that is increasing the power density, increasing the compute density of successive generations of GPU. Diversity matters. Diversity is what drives innovation. Secondly, we're going to have different workloads that we're deploying. We have training workloads. We have varying types of inference workloads. We have workloads that we need to deploy to the edge. And we need to be able to optimize price for performance for each of our workloads across all of those different vectors, whether we're doing centralized compute, decentralized compute, or edge compute. And we also need to take into account, power constraints. So the types of silicons you need to deploy on a drone that's flying overhead, for example, is very, very different than the power constraints that you're going to have as a centralized data center in some place like Abilene, Texas. So silicon diversity truly matters. If we're going to continue advancing AI infrastructure and making AI ubiquitous across all aspects of our life, we need to have a diverse range of silicon chips that are best optimized for the task at hand.
Okay, wow. So I'm starting to sense that some of the research that I was doing after speaking with you all is starting to make sense, and I see a little bit of a pattern. So it looks like where we're going to dive into might answer some of how. All right, so Hari, if I could, the AI lifecycle includes massive training runs, right? And much more frequent inference tasks where models make predictions. From a hardware standpoint, why do these two workloads present different opportunities for the diversity?
So if you look at training versus inference, as you said, like training, you can almost treat like as a superset, like wherein you need there are like different times, like there's a forward pass, backward pass, right? Okay. So there's each of them, the compute requirements are different, the memory bandwidth is requirement, and more importantly for training, the huge cluster, the scale up, the communication, we call scale up and scale out, that is a huge part, right? Which dictates like how you parallelize that. I mean, that's where your architectures dominate, right? What is the parallelism you're going to take? What model architectures you're evolving, right? Whereas if you look at inference, I don't want to simplify in the sense, but it's a much smaller set of that, actually even from the software stack as well as hardware, where it is a huge opportunity to actually super optimize, right, for your workload. Right, if you like broadly look at very simplistic view, like even for the generative AI workloads, there is primarily a decode phase, a prefill phase, and a decode phase, right, where you start the prompt. Prefill is heavily compute bound, whereas a decode is heavily memory bound today, right? So you could have a different architectures, like a slight fragmentation, and then there's a lot more opportunity to really go optimize, right? And then even for the scale up and scale out needs point of view, it's relatively much smaller there, right? So it's much more easier to run them reliably and then, right, much more for longer time. Yeah.
Okay. All right. Siona, this one's for you, because you mentioned Cloudflare is such a vast network, right? And it's completely distributed. While more hardware options might sound good, can it also mean more operational complexity? What are the real world trade-offs that Cloudflare must balance when considering a multi-vendor strategy? These are all coming from different places, right?
Yeah, I touched on that in my initial remarks. So
Yeah.
I'll just talk about some ways that we're trying to address that. And the key method being modular systems that are flexible
Right.
in terms of the hardware resources we put on the servers. Just to give you a picture, we run the same server for compute, high memory, high storage, and now inference workloads. And that's a far bigger challenge with large inference LLMs. We're able to do that by building a base compute system and adding extra storage and extra GPUs where we need them. So what we're imagining is a more latency-tiered inference as our product market segment that we're targeting, and doing that through modularity and flexibility in the architecture.
Okay. So Kevin, your turn. The current market for high-performance GPUs is then also described as a bottleneck, both in terms of cost and actual availability. From Vultra's perspective as a cloud provider, how does this concentration versus a competitive ecosystem impact the availability of mainstream enterprises, your clients, to adopt AI at true scale?
I think the good news is the challenges of the past with the supply chain have largely been solved. Mm-hmm. We're still seeing a significant amount of GPUs being consumed by some of the largest model builders. That is true, but we are no longer capacity constrained in the actual GPUs themselves. There's still some near-term capacity constraints in terms of data center build-out and power. Through 2026. We largely expect that to be resolved in the 2027-2028 timeframe as well. What's really the holdback for broader scale GPU adoption is truly enterprise readiness. Enterprises are still figuring out how to safely, securely build and deploy, in particular, new agentic AI applications. And this is where we seek to help at Vultr. You know, the early market was really focused on the largest model builders, the frontier model builders that were building very large, centralized GPU clusters, what we call a scale-up architecture, where different data science teams could schedule runs to basically build new variants of like Llama or Mistral or other models. When you look at enterprises, it's a very different network architecture, as you talked about, the scale-out architecture, and it's much more distributed and decentralized, where people are looking to truly optimize price to performance. It's not just doing one training run or scheduling 4 training runs. You're trying to run 100 different agents for 16 different applications on an inference GPU cluster that needs to scale up and scale down across 16 different regions or 30 different regions. So the architecture of how to build that out is very, very different. And so here at Vultr, what we see is we see enterprises getting ready in 2026 to start deploying at scale new what we call AI native applications. And that's where we look to help with our global network so they can start doing that at scale. But again, I think the constraint is much more on the enterprise readiness side than on GPU availability.
So good follow-up question from how the enterprises are looking to adopt a technology that's constantly changing. You're looking at it from the hardware point of view, but are you constrained also from how fast this is moving? Are they saying, we're thinking about adopting it, we're getting ready, but we don't know when to jump in? How is that affecting how Vultr approaches its clients?
It's absolutely true. So, if you look at the market, there is a whole bunch of 200 plus new providers that got capital, bought GPUs, stood up a data center, and started renting them out. And that's a lot of the people that enterprises see are potential options for them to extend their current cloud infrastructure to run their GPU workloads. But then what happens is what happens typically in an enterprise is suddenly the chief compliance officer, the CISO, steps in and says, knock, knock, let's really evaluate this vendor. Let's actually see their SOC certifications. Let's see their ISO certifications. Let's see their GDPR compliance. Let's go through all this stuff. And then the brakes come on because they're not safe, they're not secure, and you don't want to put your precious data in these companies that don't have any operating history. So that's part of the enterprise readiness. It's, there's a lot that needs to happen on the hardware side, there's a lot that needs to happen on the software side, but part of it is also just making certain that they're safe, secure, compliant vendors that people can work on. Vultr, Cloudflare, trusted vendor, Vultr, trusted vendor. That's what enterprises need to really unlock and start moving faster on, AI deployments.
Okay, well, thank you. So because all three of you are from such a company diverse background, I'm curious, we've talked about in the last few answers some of the things that have been solved, some of the things that are current challenges. So prediction time, because we're going to talk about some of those other upcoming challenges. I'd like to ask each of you, from your unique point of view, what's the single biggest challenge your company faces in the AI infrastructure in the next 3 to 5 years, from what you've learned so far? Where do you think the biggest challenges are coming? Siona?
I think if I had to pick one, it would be the need for universal interconnects that's really driven by the power efficiency constraint that we have. That's what allows us to use multiple vendors, and if we're looking at a scale-up solution, allows us to scale up to support the larger models.
Right. Okay. All right. Hari, same question. From the meta perspective?
For us, I think the biggest challenge really is how to basically, on a similar thing, one is the scale up, how to unify that protocol basically, because today there's a lot of diversity, how to make it simple and then how to drive for low latency. But the second biggest thing, what we're looking is also trying to integrate a lot more into the rack, right? Either we call as a we have another new term called like a scaling, right? Like people use like within a package, like building like a bigger, like a wafer scale integration. So that's something which we are looking at, right? Because primarily to drive the power efficiencies.
So follow up, forgive me for not understanding, but trying to integrate more into the rack?
More into the rack, as well as more like think like bringing the components closer and closer.
Okay.
All right. Yeah.
All right, thank you. All right, Kevin?
Yeah, wafer scale integration, definitely something to watch. Pretty exciting stuff to increase the density of the compute power within a single rack. But I think from the Vultr perspective, the greatest bottleneck still remains in power. Here in the United States, you're seeing an acceleration of investment in power and in data centers. Certainly that's something we're driving very hard here at Vultr, particularly on our near-term roadmap in 2026 to overcome bottlenecks in just data center capacity. But we're a global company, so inference is going to happen everywhere. AI innovators are going to be everywhere. So some of the things that concern us is what about data center build out and power availability in India? What about data center build out and power availability in South Africa? What about the same thing in Brazil, in Mexico? The world is a big place. And we're moving mountains here in the United States and really solving critical bottlenecks. But we need to be able to find a way to help alleviate power bottlenecks elsewhere in the world as well.
Right, and Fiona, you're the one who brought up power first, so I'm going to ask you, physical constraints like power per pack, power per rack, and these paramount concerns, how do these limitations shape your hardware choices? Why are open standards for chip-to-chip interconnects so critical for building the scalable systems?
Yeah, so I think it comes down to open standards, open rack designs, open interconnects, all being the path to be able to deploy something that's non-NVIDIA, which is the giant player in the market, right? Just because we build, like I was mentioning, a modular system that has a CPU, memory, and storage. And if you're using that system to attach a GPU or to scale up a GPU cluster, then the network and the interconnect will become your bottleneck. And the more standardized it can be, the easier it is to deploy. And going back to the operational burden in terms of planning all the way through deployment, much easier to do if you're, let's say, using open rack designs, right? You just roll in the rack you want and roll out the rack that you are refreshing.
Right. That makes so much sense even from my world, because in our software world, I work a lot with the Vice President of Open Standards at the Linux Foundation, and every single project that they're bringing forward in the software world for standardization is helping them move forward more quickly. So that absolutely makes sense. But not just power as in the full power, but the powerful chips. Hari, at Metascale, it's not just about having powerful chips, but squeezing every last drop of performance, right? What are the key technical bottlenecks that must be solved to keep up with the pace?
So it's a good point. So primarily, like today, if you look at the generic GPUs, they call something called MFU, like a model flop utilization. So that typically, like if you look at most of the workloads, that percentage is very, very low, right? So let's say if you're able to extract from the same chip, like let's say you're able to bring from low 40 to like 60, 70%, you're actually, it's like a compute multiplier there, right? So for us, like similarly, so identifying those compute multipliers and how we go after them, actually, especially for these different workloads, presents a huge opportunity, right? And also, like when you're talking about bringing in more and more components together, also the power density is also increasing a lot. So the thermal, the cooling, and everything also becomes a huge investment, right? So now the chips are not anymore 1 kilowatt, right? They're going to 2 kilowatts or 3 kilowatts, right? Each package, right? So now getting the new thermal solutions, new materials, right? The packaging world, developing those, actually, that's also becomes very, very critical, right? To enable these solutions.
This is a comment from some of us who have been around for a long time, but it reminds me of the late 90s chip wars, right? Something along those lines? Yeah, okay, all right. Siona, physical constraints, I'm sorry, I got the card mixed up. I was trying to go by the order that you guys were talking about it. So for Kevin, Vulture's in the business of building out this infrastructure globally. What are the major economic and logistical challenges in meeting the explosive demand for AI compute? It's got to be more than just power.
Yeah, it's definitely more than power, and it's actually even more than the GPU, because I think, as was highlighted, the CPU still plays a critical role in inference. I mean, you also have to remember, CPUs are going to power a large part of, RAG pipelines as well. It's still the core infrastructure that runs your vector store, for example. It's still running your application experience. So one of the economics challenges is, we need to not only upgrade and distributed GPU clusters for purposes of inference all around the globe, but so too do you need to upgrade all of your CPU infrastructure and tightly couple your CPU infrastructure with your GPU infrastructure to make it simple and easy for people to deploy new AI native applications. I think there's another challenge as well, which is we need to make it easier, because right now standing up GPU clusters is very much, it takes like a PhD in most platforms, and that's what we strive here at Vulture to simplify. Any student in college should be able to easily harness the power of open source models like the models coming out of Meta like Llama, and build and create new things with little to no training. In the core cloud native world, we make it super easy with serverless platforms to, simply code and go. Why can't we make, building and operating AI native applications across distributed clusters of GPUs and CPUs simple and easy? It shouldn't be as hard as it is. And here at Vulture, we're trying to change the economics of development of AI native applications by literally making it so my grandma can do it. Why can't my grandma vibe code an AI native application and just have it run everywhere?
That would be amazing.
Of course she should be able to do it. She's pretty smart. I mean, she's very old, but she's very smart.
Absolutely. More experience than any of us.
More experience with age.
Exactly. All right. I like it. Siona, let's talk about where AI happens. Does every AI task need to run in a massive centralized data center?
No, I think Cloudflare is a perfect example of it's not necessary. And I think it's important to think about inference and the market opportunity there going forward, which is where we're focused. We're not so much in the training space.
Okay.
And with inference, latency is very important, as we all know. And eyeball latency is our true KPI that we build for. So that is enabled by a decentralized distributed edge network. And we're honing in on our competitive advantage that existed before inference was at play. So I think it's a different, we were talking about training versus inference and different workloads and different needs. Inference is, I think, more latency bound and distributed.
Okay, so for which one is it better to be a little bit more localized? What are the opportunities there?
With inference, I think inference is a more distributed workload by its nature.
Okay.
There is also an opportunity for distributed training in the future. And another interesting thing that we've been looking at is a disaggregated architecture where you separate out your compute and your memory and your storage and your GPUs, right? Especially when you have an edge network that's everywhere and you can't afford to up-level your network and each one of your components in each of your sites. I think that's a very interesting area in terms of architectural improvements that will benefit us longer term.
Okay, so really for anybody who wants to jump in, you were just talking about...
Yeah, let's give a real world example of this where you need a distributed architecture. We live here in Florida, we have hurricanes, right? And we have the bright line. What happens after a hurricane? How do we make sure that the rails are safe and that the bright line's not going to encounter some sort of obstruction? Well, nowadays you can fly a drone overhead. And that drone could be doing real-time computer vision to identify whether there is an object on the track. That actually will happen on the drone itself. That's like a custom silicon that's running a limited computer vision model on the drone itself, so it's doing real-time object detection on the rails as it's flying at high speed along the length of the bright line, because the bright line needs to run. But meanwhile, it needs to have local inference capabilities, because if it detects an object, it needs to hit a model that's here, like in Miami, that's close by, to basically identify, is the object a hazard, not a hazard, and if a hazard, send it off to some agent that can identify what that hazard is and then schedule an appropriate workflow based on the priority to go out and fix it. So you don't necessarily want to be round tripping that, because that decision making has to happen in a split second, because that drone is flying fast overhead. So identify the object, prioritize the object, move on, right? Another good example is like, I was speaking to a drone manufacturer that does this exact same thing. We had those horrible floods in Texas, right? Do you know how many lives could have been saved if they were able to just quickly throw up a drone and do real-time computer vision and have local inferencing capability to identify body, still alive, get a crew out there right now? It took them days to go up and down that river. Like, that should have been done in 15 minutes. That is the power of having local inference. Real time, it could save lives, literally.
I think it's worth noting how this increases the complexity of reliability when you have a distributed network and you have diverse silicon that you're deploying everywhere. You want to make sure the snapshots you take, if you're doing a training workload or where your data is stored, is cached appropriately, so you're not losing the latest if you're on the inference side, right? And I think it's a challenge we're trying to solve at Cloudflare, and I imagine same with you.
Right. Hari, thoughts?
I mean, for me, like, as I said, like on the inference side, there are two things, right? Because even for us, like, because our users are spread everywhere, we run like a similar resilient system, right? Because inference needs to be everywhere. So like whenever something goes wrong, kind of a thing, immediately how do we steer all the requests to the different one? So that's how we look at it. So whereas training, it's much more like the biggest problem is there's a huge one big cluster, but reliability running, because keeping the downtime to minimal is the most important thing.
Okay.
Right, because today, the reliability, like there's so many components involved. So any component going down, how we go and backtrack, and then how do we roll and then start again? I mean, all of that boils down to the throughput. Right.
All right. Well, just to make sure we cover everything, though, let's talk about the tailored part of the title of this panel. What kind of architectural trade-offs are made when designing custom silicon specifically for inference versus using the general purpose GPU built for training?
So for inference, I think the key, right, even if you look at today's workloads, like especially right now, because as the agentic AI starts going up, actually the inference, the demand will be very, very high. So there, if you look at primarily today, even though we don't know exactly how the distribution varies, let's take the simple a video gen, most of these are around the video gen, right? So there we call the LDM models, and also similarly for prefill with long context, actually, it's all very, very compute heavy, right? And also the compute can be you think almost we can put a monolithic, this is something like the matrix multiplication, they are very huge matrices. Right. So you can treat that as one tile, so you can have very, very dense compute there. And the memory bandwidth required is very small. All right, so you could really customize a solution where we really don't need the expensive HBM memory and other things, right? Whereas, if you look at other portion, for a typical a large language models, right? There's a biggest portion for a token serialization and the need for the flash attention, the self attention, right? So there's a lot of a memory bound workloads. So there you don't need as much compute, but you would like to have a lot of memory, and then you could have very, very specific custom built compute, very close and very efficient to the memory, right? So we could have a lot of this divergence as we understand the workloads. There's a lot more opportunity for inference.
Okay. Fiona, anything to add or?
We don't build custom silicon, but somewhere in the semi-custom area. And I think the open ecosystem with chiplets, ARM is building something super interesting from our perspective, where they take different IPs and you're able to choose which ones you want and integrate that into an SoC. It's called chiplet designs and subsystem designs. It's a great way for us to optimize for the workloads that are interesting to us without having to spend the kind of money that would be needed to build a fully custom solution.
Siona, that makes absolute sense. Right, exactly. Kevin, what about for you?
Yeah, so when you're thinking about a distributed global network, you want to get out as close to the edge as possible. This is always true in, the long arc of compute history. We're constantly moving further and further out to the edge, distributing compute to where people live and work. And in cloud native applications, most of our cloud native applications run, if not at the data center edge, at the full edge, right? So too, we need to do that with AI infrastructure. And what this means that when you're distributing compute nodes, like literally in metro regions, there are necessarily power constraints. And so sometimes you need to cost optimize for lower power density in your racks in order to serve specific types of inference workloads. So for those workloads that can run on, simpler silicon that requires like lower power density so that it can actually fit directly in the heart of a metro region in an older data center that hasn't yet been rebuilt and, upgraded, then it can always fail over for heavier duty workloads that are in brand new data centers with the thermal cooling that can run the latest and greatest GPUs. So again, this gets back to diversity and just having a heterogeneous architecture, and then being able to, from a cloud provider perspective, make it seamless to end user, because the end user shouldn't care. Because the end user should just basically vibe code, go deploy their model, and the thing just works. And then to the extent that we can actually run that model on higher performing infrastructure that's also lower cost, as close to the metro region as possible, that should all be abstracted from the user. They shouldn't actually know or care.
Got it. Okay. All right. So just to wrap up, each one of you, we have just a few minutes left. Is there any closing thoughts around where you think optimistically we might be headed? What's coming up the road? What you're looking forward to?
Yeah, I think in 5 years, at least for me, I think on the hardware ecosystem and software, right now I think we are already seeing that the barrier for the software, like earlier, like the biggest advantage for the initial GPU is the bigger the software, right? So that lock-in is going away. So I think in 5 years, especially like with the AI becoming better and better, you can see that that problem will be solved, I think, right? It's very easy to like even deploy like with the Pythons and the Triton and other libraries, right? It should be able to very agnostic. You can bring up any diversified hardware very soon.
Okay, thank you, Hari. Siona.
I think anything that enables more power efficiency is very valuable to us. I touched upon disaggregated architectures. It could be just an inference card that's low power, but allows you to scale up and down as needed with the interconnect, etc. It could be a hierarchical memory solution, which is also something we've seen, where you're not entirely reliant on high-cost HBM, and you're able to use the DRAM or larger capacity memory to get the same level of performance. So I think all of this rolls up into what enables more power-efficient inference from a distributed network perspective is super valuable.
Okay, thank you. Kevin, bring us home.
Yeah, so I have like a little bit of a different statement, which is I think the most important thing is like, we're at a unique point in time in human history, and where we have the ability to change the world. And I go back in my career 30 years. I started my first company in 1996 when the Apache web server was released, and created a web content management system called Interwoven TeamSite. And then that was the dawn of the web, and the web was very exciting. We started laying all this fiber, we started upgrading our infrastructure, we started actually building new data centers, and we started distributing web applications outside the home office and actually in colo facilities, and that was a really, really cool time. And this is 10x, 100x what that moment in time was. Think about how much the world has changed because of the web. Think of how your lives have changed. Like, we don't even know what our lives are going to be like in 10 years. And I think just as a community, we need to work together to make sure that we do good things and that we uplift the whole of humanity and change the world and make it a better place. Because I would argue that we've done that with the web, but we also unleashed some forces that maybe were not so positive. Mm-hmm. So let's do a better job this time. And let's make the world a better place.
Thank you. Thank you, everybody. Thank you for joining us.
Thank you. Thank you.
Thank you so much.
Thank you, everybody. Have a great day. Have a great conference.